Let's call it Florin Ballas from New Age Networks. This is pretty interesting. Basically, what a lot of us have seen in data center networks is that the concept of cloud, however you want to apply that term, and what we think about in physical networks, we haven't really brought together, right? We've kind of hacked together. Hypervisors have virtual switches. You have your physical switches. There's not really an interoperability between that layer, and so interested to hear what movement's been made in that space.
Thank you. I'm Florin Ballas. I'm responsible with product management at New Age Networks, and I'm here today to talk about some interesting development in the cloud networking space. And I've been through a number of technology cycles during my networking career, probably 8, 10, and I think this one is by far the most interesting one. And I think part of it is the fact that in the cloud networking space, we have basically people that own the cloud networking and the compute part. And they worry a lot about the application performance, about application developers. So I want to start with the application developer view of the network. So for most application developers, the networking is a black box. They send packets in, they get packets out. And I think Peter Deutsch in '94 brought up this very interesting set of fallacies of distributed computing. And I thought they were really funny. That's how the application developers see the network. It's reliable, latency is zero, bandwidth is infinite, so on and so forth. And for us who dealt with network engineering, we know that the network is more of a living organism. Some colleague told me to say it's like a wife. It's not that simple, right? And whoever did network engineering, at times it seems more like an art than an exact science. But for them, it's more like this stuffy, fuzzy thing that should deliver. Now, I wanted to bring up some interesting studies, some fellows from Microsoft cloud networking part put together. Basically, they took a MapReduce task. MapReduce is basically an application that splits basically a huge transaction between multiple compute resources and then consolidates the results. So it involves millions of transactions, and they put it into a very well-contained, small enterprise data center environment where the compute resources were next to each other pretty much. And it did complete in 4 hours. So they calculated, looking at the cost of a popular cloud compute, that it should cost about $100 to run it there. And then they run exactly the same task into that cloud environment. And to their surprise, it took actually 10, 16 hours, which meant cost of $250, $400, depending on where exactly they run and how the compute got instantiated. So they came to the conclusion that actually the cloud networking is in the way, and it influences radically the application performance. As a result, it could become a barrier to entry of enterprise IT guys into cloud when it comes to expanding their application to the cloud. So data center network virtualization came to the rescue, and it was supposed pretty much to deliver the easy button and do the nirvana of networking, right? And people throw billions of dollars in Silicon Valley at the problem space, and we are really enjoying that environment in there, so I shouldn't speak negatively about it. But I want to go one level down and talk about the details, because I think the devil is in the details, and basically see what is really required, more than just basic data center network virtualization. So I will start with the layer 2 service virtualization, which is the state of the art today, right, in the cloud networking space. So if you look basically at the first generation of data center networks, they were pretty much using VLANs to do subnet isolation. That allowed them to also do multi-tenancy to a certain extent, because you can overlap the IP space. Everything was good. But they soon realized, and this is stuff that the telcos realized in like 2003, 10 years ago, when they tried to build Metro Ethernet, that VLANs have a lot of limitations when it comes to basically a scale deployment. So for the data center space, what was actually surfacing first and what people saw easily, VLANs are based on a flat domain, right? There is no tunneling, nothing. All the core switches handle per VM state. So you have the MAC-FIB scale with the number of VMs. So that limited them a lot because they also deploy cheap data center switches and they won't roll back, right? And they had limited FIB sizes. And the cycle to change the data center network is pretty long. So it was a deterrent to cloud evolution. Then everybody knows that spanning tree, it's basically not stable enough for a large Ethernet switching environment. And I would argue that multi-chassis lag, having engineered some networks with multi-chassis lag years ago, it's actually not manageable when it comes to end-to-end loop avoidance. So pretty much I will go into technologies that were developed for the cloud networking space. And I'm not talking just from a vendor perspective. This is work we did in a number of standard organizations in the IETF and also in open source to develop those technologies. So I'm going to just summarize them for you and bring up some debate points. So layer 2 network virtualization, I gave in there some examples. It's the VMware VXLAN, the Microsoft NVGRE. Basically are supposed to address the layer 2 segment in a better way than the VLANs. So the way it does it, basically, you use some virtual bridging instances that could run basically into the hypervisors or into the top of the racks, and then a bunch of overlay tunnels. So the data center networks just runs IP, and does not keep per VM state. So this is something we did in VPNs a while ago, but it was adapted to fit what they wanted to achieve in the data center network. And this is good. So we achieved some stuff with this particular development. But in the rest of the presentation, I will argue that it did not go all the way to address and provide a full cloud networking toolset. And I'm going to talk about these 4 issues and limitations, and then I will follow up with what we believe is the solution for them. So I'll talk about the enterprise real use cases, how complex they could be. And I will talk about bandwidth and routing efficiencies, and then about complexities from a networking toolset perspective and operational perspective. So basically, the layer 2 only virtualization view of an enterprise network topology is that the main thing is the subnets, right? So you have subnets to play with, and then you fit in between different pieces as you can. Now, I know you can't see very well what's going on in there, but this is kind of a usual enterprise topology. And briefly described, you have the external wide area network, internet at the top, and then the blue boxes are different application servers running. So you will have usually at the top web servers, then a business logic. You can have some storage down there. And the red lines are firewalls. You can have a load balancer in a mixed DPI, all kind of stuff, right? So you could have 3 layers of firewall. This is actually usual. And you have a DMZ zone in the mixed. So this is the reality and what you need to address to actually remove the barriers to entry for the enterprise in a cloud networking space. And to go a little bit simpler on these use cases, pretty much what I said could be shown in this particular picture. So you have basically an internet router, a firewall offering a DMZ zone, some routing, subnets, VMs offering web services, and then VMs offering business logic underneath. And you can have an internal firewall. And I didn't show the load balancer in the picture. But that's pretty much what they are trying to do in there. And remember, many people talk a lot about subnet connectivity. The subnet in the cloud space is not provided necessarily to make the web servers talk to each other. They don't do that. They talk to the business logic or to the outside world. The subnet grouping is to handle easily the policies. All the web servers get a policy. Talk to the outside world on a certain port, for example, and to the business logic on a different port. So there is a policy and security framework aspect to this organization that is very important. And then there is the hybrid cloud that everybody is talking about. An enterprise with sites with their own data center and applications running there, and they need to burst out into the cloud provider space. And they do that using VPN, IPsec VPNs, but there is a lot of investment on IP VPNs and VPLS And they like those VPNs because of the security, SLAs, reliability. And a solution needs to basically provide the expansion of these VPNs to cloud services, and while maintaining the whole network automation. A variation of that is the case where they want to expand the subnets between the data center and cloud provider data center. They want to do that either for disaster recovery, they want to maintain the subnet when they push VMs around, or because they felt comfortable in the WAN with VPLS and they want to maintain the layer 2 extension. We hit those kind of use cases again and again. So now I will talk a little bit about bandwidth latency issues and the effect on the overall cost of the networking and application performance. So remember, in the layer 2 only virtualization, they have subnets that they offer and control. In reality, you need at least some layer 3, and most of the time you need L4. So in either case, the cloud management systems like CloudStack, OpenStack, VMware vCloud, they instantiate the layer 3 routing on a virtual machine. And they could have 2 of them in there. If you see, there is another one on the right side. And that is active standby backup. They don't even have VRRP. But basically what they do, every time you have to go from the red subnet out to the internet, you have to go all the way back into the VM and then up into the internet router. So that takes a lot of bandwidth 2 times from your data center network and increases the latency. So the first time I saw it as a networking guy, I said, what's the big deal? But when you have millions of transactions and they expect fast response time, that starts to add up and matters. The same thing if you want to go between subnets. And it's very interesting. We actually activated VMs in a popular cloud. You can do that with your credit card. And put them in different subnets and try to run a ping between them. And at times, you can see variations, because even if they are inside the same server, they could be instantiated inside the same server, they are still going through the layer 3 router. And on the right side, I show a case where they instantiate the routing on the top of the rack. That could happen, but nothing changes. It's the same thing like the VM. Traffic tromboning happens, and you are limited to the resource offered by one particular virtual machine to do this layer 3 routing. And application performance could be a deterrent for cloud services adoption. So these issues were actually highlighted in IETF network virtualization over layer 3 working group. So I will have some references at the end to that work. And a variation of this is the case where they just put all the routing on top of the data center gateway router. And the data center gateway router, it's usually, the interfaces are like 10 times the cost of the interfaces on the data center core devices. And so it's very expensive to actually take bandwidth from the router every single time. And of course, the application performance suffers. It's the same kind of issues. Now, in terms of network complexity, so remember where we started with the layer 2 service virtualization. We wanted to get rid of VLANs, right? And I'm taking a use case where we have the 2 subnets, a web subnet and a business logic connected with a router. If you want to instantiate that in a data center domain, you usually have the red VMs and the blue VMs interconnected by a router VM out there. And now, if you go inter-subnet, it's fine. You can use the layer 2 over IP tunneling encapsulation, either MVGI or VXLAN. When you go to the wide area network, guess what? Everybody is back to provisioning VLANs. You need to translate the encapsulation. So you're back to provisioning VLANs, you're back to automatically deleting VLANs, which actually it does not happen. People usually go back to flooding and put VLAN trunks in there, which is basically creating other kind of issues for data center network. So now I will talk about some particular implementations that I saw out there, and then the IETF draft on VXLAN. If you look at what VXLAN requires, if you read the draft, they were saying there that in order to basically handle VXLAN flooding selectively, you need to go and put multicast in the data center core. So you're back to running PIM and IGMP snooping, which is not okay with most of the folks I've been talking to in the data center. They don't have multicast enabled. More importantly, remember we try to solve the tenant state in the core. we wanted to take that out from the core of the network. In order to provide proper flood control, you need to go back and actually instantiate per tenant multicast groups in there, or at least some kind of like multicast state that follows the tenant grouping, which is basically something that, in our opinion, is not good for the overall service scalability. Now, I wanted to talk briefly about an issue that is often overlooked, but is actually very important. And it's a real issue today. So the operational issues, the OSS nightmares. So if you want to connect services in a data center administrative domain, to basically a wide area network domain, you have to go through a telco offer, right? And today the handoff is VLAN based. And the way you provision these VLANs, you need to provide an interface between the cloud management system and the OSS system. And OSS doesn't stand for the highly automated open source system. It's actually the dinosaur of all dinosaurs, whoever is familiar with telco OSS. It takes months and years to actually write code inside that system. And basically to go from a highly automated cloud network environment to the OSS environment, you basically get the common denominator. If you look at the Amazon VPC Connect service, right, you actually have highly automated service in there, but then you have to go and do the VLAN handoff. And that's basically the only way to do that is by getting people in the mix. So it takes, again, days, months, whatever telco system is present in there. So it's a big deterrent. And of course, it increases the complexity of enabling services on a dime. Many people want to burst during like particular times of day even into the cloud. So, we summarized those requirements into those 5 pillars. So I fully agree with the rest of the industry here, I think. IP is the way to go. IP is scalable, it's well understood. IP is the core and the standard in the internet and wide area network. So we believe that's what's going to make it into the data center networking from a core perspective. The tunnels will be IP-based. Layer 2 multi-tenancy, it's a good development. Nobody says it's not good. It's basically a way to do the subnets without doing VLANs in the core. I believe we need to go up the stack and be able to provide a mix-up L2 and L3 and potentially L4 services into the service offer. We have to go beyond that. And to eliminate the barriers to entry for enterprises, we need to expand the VPNs to enable cloud services, to interact with those VPNs, and eliminate the operational complexities. And at last but not at least, I wanted to briefly touch on SDN programmability. I think it's a must. And I think actually it's the most important development we got from the cloud networking work. And many people maybe think about SDN programmability as the capability to take a bunch of 5 tuples and distribute them throughout the core switches and routers. And that it's a valid use case for academia or for people that have specific needs. That's fine, could be used. I think though, we need to go way beyond that with SDN. And the advantage in my mind, it's better described by an analogy I was thinking about while walking here. Writing basically individual 5 tuples and creating flows, steering flows, it's like basically using assembly language to write programs. I think, we need to get to what Java did for software developers. I think SDN should give us that sort of tool set for networking. And that's what we need to strive for. So when we look first at these 5 pillars, we thought, okay, 2 years ago, I was like, okay, we already did this in the VPN. We started in '99. We developed IPVPNs, overlays, solve all of these issues. What's new here? We have thousands of networks running them stable. We should be able to do the same in the DC. Then talking to people, we realized there were some issues by just porting this tool set. First and foremost, the cost points were different. And then people mindset in the data center is not good for deploying MPLS. They think it's too complex. They are okay with IP, but they don't want to go beyond that, right? So we had to rework basically the protocol stack. And there was a lot of good work done in IETF on that. And a lot of bridging that happened between the cloud open source guys and the hardcore networking guys in there. So I think we came up with a good compromise in there. And I think while we are doing all of this, we have to keep in mind the rich toolkit we got from VPNs and the lessons we learned. So the solution, I believe, is basically the capability to distribute L2 and L4 capabilities down into the data center as required. So if you look at the usual data center architecture with the compute racks and storage racks connected via the data center network, starting with the top of the rack, the blue item, basically, I think everybody is kind of on the page that IP core, it's a good idea. Amazon actually did it way before we started to talk in IETF. And they did a very good job eliminating VLANs. A great initiative, right? Then basically what we developed in IETF the concept of network virtualization edge, which was similar in a way with the provider edge device. That's the place where the overlay is initiated. And this NVE function could reside in the top of the rack or could be distributed between the hypervisors. And the same topology I was using before, the simpler topology with 2 subnets and a routing, could be represented basically as a bunch of router functions or L2, L4 functions, router, switch, and ACL functions distributed across these NVE elements, where the blue and red VMs are present. Now, diving a bit inside the architecture, basically, if you look at, on the left side, I'm using a bunch of racks that you usually find in the data center, compute and storage racks. That could be a certain area of the data center. And then you have an IP core interconnecting this domain with the rest of the network or with other data center domains. In the control plane, this data center is being programmed by basically a number of controllers. In this case, I'm showing 1 or 2 controllers for redundancy, who are talking to the forwarding elements. And they could be using OpenFlow, or they could be using proprietary API that maybe appliance vendors are implementing or hypervisor vendors are offering. They know what's going on in the data path, and then they have a northbound interface using APIs to the cloud management system, like to vCloud, OpenStack, CloudStack systems. And they use all of this information to actually instantiate data path between the compute resources. Now, when it comes to an additional data center domain, located in the same place, in the same location, or maybe across the world, you will need an additional controller, SDN controller. And this SDN controller basically will take care of his own compute resources from a data path perspective. Now, how do we basically make the 2 data center domains talk to each other? What we are talking about in IETF is to use basically multi-protocol BGP, which is a protocol dear to the usual NANOG audience. So BGP has all the functions, all the required functions. We added also some layer 2 functions to BGP to be able to distribute the information and at the end of the day basically establish the data path between data center domains. It's standard, everybody supports it, and it will allow multi-vendor controller interoperability. And in the data path, BGP also has the capability to control multiple types of encapsulations. So when you go to a provider edge device, pretty much MPBGP is the best tool we have around to do interdomain exchanges, right? You don't need basically the service provider OSS interface. Everything can be automated, and we take the humans out of the equation. Moreover, this SDN controller, if you think about it, makes the whole data center domain appear to the rest of the networking world as just a regular router or provider edge device. It hides the nature of the data center domain. And more importantly, it could also take the VLAN handoff inside the data center out of the equation. You can provision whatever encapsulation you want, and whatever the provider edge device or the router understands, and could do that automatically. So, using MPBGP basically allows us to interconnect data center domains from different vendors, and when I say different vendors, I'm talking about cloud management systems, hypervisor vendors, and could belong to enterprise or cloud provider. It enables the hybrid cloud in a smooth way, and while maintaining the cloud network automation. So I reference here a number of drafts that describe the issues I covered at the beginning of the presentation, and then I have the draft describing the federation of SDN controller at the bottom. I will be more than happy to get feedback on it from you guys. And by the way, the OpenFlow specification work is very important. And I submitted the slide before thinking about updating all of this. So some of the drafts, you need to search for the names on the draft. The versions might be a bit outdated. So just to put everything together, in summary, Layer 2 service virtualization, I think, is great, but it's a small piece of the puzzle. I believe, in the industry, we need to focus right now on actually addressing the whole puzzle. And at NANOG Networks, we are basically looking to address this puzzle and to provide a complete solution. But more importantly, I believe we are going beyond providing just the Java toolset from an SDN programmability. I think we came up with something much more interesting than that. And I will be very happy if you guys will come during lunch or afternoon to discuss a little bit about the details. And right now I have about 8 minutes left. I am between you guys and lunch, but I will be more than happy to entertain some discussions, some questions, if you guys have any. Jeff, thank you.
Hey, Florian. Justin Sura from Ericsson. So we've heard before BGP is the best IGP, and many people here run BGP everywhere. What do you think about XMPP from lower part of the network to the edge, instead of BGP, which is not so easy protocol to implement properly and run?
Okay, so I think XMPP fits into the controller to hypervisor place. I don't care about the protocol there. Whatever the endpoints support, that's what people are talking about XMPP. And to me, that's fine. If it fits in the environment, it's absolutely fine. I think what we need to keep in mind is the open source guys, they already are doing a lot of development. So to me, to bridge the two worlds together, I'm talking about using MPBGP to talk out to the wide area network, and towards the hypervisor, whatever they develop, we should be able to support it. Whether it's XMPP, OpenFlow, or their own APIs, whatever. I think important, though, for the hypervisor part is that we need to make sure that whatever we do in there gets distributed by the standard open source guys, right? It's part of the standard distribution. That's what the hypervisor guys love to have, something that is already in the distribution. Any other question?
Okay.
Okay. Thank you very much. We appreciate it.
Thanks very much. Just the usual reminder about the survey. NOG Lab is now closed, but invite you back after lunch at 2:30 for a couple of great talks, and then we have the peering track in the room directly next door starting at 4:30. Thanks, everyone.